it's fine. So we want to take a look at this particular question, and it says a light elastic string has natural length A and modulus of elasticity 12 mg. One end of the string is attached to a fixed point or the other end of the string is attached to a particle of mass m. The particle hangs in equilibrium vertically below or the particle is pulled vertically down and released from rest with the extension of the string equal to E, where E is greater than a third of A. It says in the subsequent motion, the particle has speed the square root of 2GA when it has ascended a distance of a third A. Find E in terms of A. All right. So this is a very nice question, and we would want to take a look at it. All right. I'm just going to maybe kind of illustrate what they have given us here. So we right here have a string attached to a fixed point. Okay. So, and a particle right on here. And they've told us that the natural length of this string, okay, is A. So we have A here. The modulus of elasticity is 12 mg. They've told us. So all this information, we're getting it from this very first line. They then say one end of the string is attached to a fixed point or, all right, which means that we have the point or here, that's the fixed point, right on here. And they say that the other end is attached to a particle of mass m. So here's the particle of mass m that we got here. Then they say that the particle hangs in equilibrium vertically below or. Okay, so this is what we have. So we actually are in equilibrium right here. Then the particle is pulled vertically down. So here they say that it is pulled vertically downwards, maybe to some certain point, all right, and then released from rest. Okay, so actually the rest is here, which means that it starts with a speed of 0. So let me just say the speed at this point is 0. Okay, with the extension of the string equal to E. So the extension at this point, that is from here where its natural length is, down to this point where it is released from, we are being told that the extension is E, all right? And then what else do they tell us? And they say E is greater than a third of A, right? And then they say, in the subsequent motion, the particle has a speed of the square root of 2GA when it has ascended a distance of a third A. But we shall take account of all that as we go. But what we're going to make use of is the fact that we're actually going to use the concept of conservation of energy. And according to this concept, we can put it this way. Okay, in simple terms, the initial energy should be equal to the final energy, basically. All right. So this is a very simple way to understand the principle of conservation of energy. The energy we have at the initial point is equal to the energy we have at the final point or instance. Okay. Let's start with the initial point. Okay. The initial point is going to be here. All right. This is the initial point. Let me just call it I for initial. All right. So at the point I, okay, the initial kinetic energy is 0 because we are starting with the speed v of 0. The initial gravitational potential energy is also going to be 0 because we are going to assign this starting point to be h is equal to 0. Okay, so if h is 0, then it means GPE is also 0. Then for the initial elastic potential energy. I'm sure you can recall that for elastic potential energy, we calculate it as lambda x squared over 2L, right? Do you still recall this formula for elastic potential energy?
Yes, sir.
Okay, that's perfect. So in this case, lambda is 12 mg. So we have 12 mg here, and that's going to be times the extension, all right? And the extension here is E, okay, for the point I. So that's of E squared, and that's over 2 times the natural length. The natural length, according to the information given, is A, natural length A. So it's over 2A. So this is what we're having here. And this has to be equal to the final energy. All right, so I'm going to do this. Okay, sorry, let's continue. So that's going to be equal to, for the final energy, okay, let's just have something like F somewhere along the way after the particle has been released. So say it is somewhere here. Okay, so this is the point F where the particle is. And at the point F, we have been told that in the subsequent motion, the particle has a speed of the square root of 2GA. So the final kinetic energy is going to be half times the mass of the particle, which is m, right? And times the speed squared, so root 2GA squared. That's going to be plus. Now let's have the final gravitational potential energy. So now the final gravitational potential energy is going to be influenced by h, okay? The distance from h equal to 0, that is. And we've been told that it would have ascended a distance of a third A. So h in this case is a third A. So we'll say it's mg times a third A. So that's basically what the final energy is going to be. All right. I hope you're tracking, you're following.
Yes, sir.
Okay, that's fine. And that's going to be plus the final elastic potential energy. When you talk of elastic potential energy now, we are going to use lambda, that's 12 mg. And we're also going to need the extension from its natural length down to here. That's what the extension is going to be. So that's basically E minus a third A. Remember, E is the whole extension up down to I. So for this little one, we'll say that's E minus a third A. Okay, so that's going to be E minus a third A squared over 2 times the natural length 2A. What do you think of that? Do you get that?
Yes, sir. But I understand how you calculated initial energy.
Okay, so let's go back to initial energy. Okay, we're talking about I, all right, the starting point. That is where the particle was released. Okay, so we are here, right? And when the particle was released, they say that it was released from rest. You see what it says here? So if it was released from rest, it means its initial velocity is 0. So that's why we have the kinetic energy to be 0. Do you get that part?
Uh, yes, sir. Um, my question is, you said the extension is the length E, right?
Oh, yes.
And from the diagram, from V equal to 0 to the other side where it's somewhere between the particle and the string, right?
Yeah. Okay. So, all right, it's fine. So you want me to, what you don't understand is why we used E as the extension?
Yes, the whole distance. I don't understand why is it going beyond the mass m.
Okay. Okay, I do understand what you're saying. All right. Okay, so let me explain it in two ways. The first thing that you need to understand is that the reason why we used E as the extension, even without using the diagram, is they say it in the diagram. They say when the particle is released from rest, the extension of the string is equal to E. So that mere reason, okay, qualifies us to make use of E as the extension. Right. Secondly, looking at the diagram, the natural length, I marked it at here, okay, which means anything beyond that is extension. All right. So when the particle is stressed all the way down to I, its extension is going to be E. All right. So that's again the reason why we're using E. I've just taken that from what the question says, right? Now, if you look at the point, this point here, it's the starting point. I've just taken it to be the starting point, like when the particle is in equilibrium, because they say that the particle hangs in equilibrium vertically below O. So they don't necessarily say that it is hanging in equilibrium and the length of the string is A. They don't tell us that. So I just took it to be hanging maybe at some point where there's a little bit of a stretch. Okay. So, but you shouldn't worry much about that because in this particular question, that does not really matter. So what should just matter is the fact that after it has been pulled down, and it goes to the position I, the extension in the string is E. So that's why we just consider that to be E. Okay, I don't know if that helps.
Yes, sir, that's okay.
All right, it's okay. Let's continue. Let's carry on then. Um, what we now need to do is simply, well, simplify what we got. All right. Starting with this part, 2 goes into 12. How many times? 6 times, right? So we're going to be having 6mg e squared over a. Okay, that's what we have on here. And that's equal to, we can simplify this part. Squaring this, we get 2ga. Half times 2ga is ga. So we'll be having something like mga just from simplifying this part. From simplifying this part, we get a third mga. And simplifying this part, we will simply be having 6mg of e of minus a third a squared o over a. I'm actually going to take this to the left, all right? Okay, I'm going to take this to the left side. So, and I'm also going to factor out 6mg a, actually 6mg over a. So let's do that. So if we factor out 6mg over a, on here, we will only be left with e squared. And when this comes to the left, we'll be having a minus, and that's a minus of e minus a third of a squared. Okay, like this, close bracket. Okay, and that's equal to adding this two gives us 4 over 3 mga basically. All right. So already I can see that we can divide both sides by mg. So on the left side, we'll be left with 6 over a off and expanding here, simplifying, we'll be having, okay, let's just say e squared minus expanding this. That's e squared minus or plus 2/3 ea plus, so minus a ninth of a squared. I've just expanded that bracket and taken into account that there's a minus sign, all right, in front. So all this is equal to 4 over 3 of a, all right. So we have 6 over a of, here e squared minus e squared is 0, okay? And we have 2/3 EA minus a ninth A squared being equal to 4 over 3 of A. So let's multiply both sides by 3A. This side by 3A and this side by 3A. If we do, we know that the A's cancel. 6 times 3 is 18. So we have 18 of 2/3 EA minus a ninth of A squared being equal to 3 goes into 3 once. So we have 4A squared remaining on the right side. Let's multiply 18 into the bracket. We will get 6, 12, 12 EA minus 2A squared is equal to 4A squared. Okay, so this is the same as we have 6A squared minus 12EA or AE equal to 0. We can factor out 6A, so we have A minus 2E here equal to 0. So it's either 6A equal to 0 or A minus 2E is equal to 0. Okay, remember the question says we should find E in terms of A. So here we can say that 2E is equal to A, and E is A over 2. So this should be the answer. Okay, that's how we can express E in terms of A. Okay, what do you think of this? Did you understand it?
Yes, sir.
Okay, any questions on what we did? It's all good, you think?
Yeah.
Okay.